Hello everyone, today I will talk about routing, uniform cost multipath routing for reconfigurable data center networks. This is a typical topology of a data center network. The bottom lies the servers. Above the servers, we have different levels of switches, such as top or red top switches. All these switches are electrical switches. However, with the emerging cloud workloads, electrical switching is limited by the low switching capacity and high power consumption. Optical switching is a promising solution to replace electrical switching, and now is gradually deployed in production data centers. Optical circuit switches are used to construct dedicated circuits among TORs. With optical switches, the topologies can be reconfigured, and we call them Reconfigurable Data Center Networks, or RDCN. We can use the following diagram to represent an RDCN. The nodes represent TORs, and the number over the edge represents the time slice, meaning when these two TORs have a circuit. RDCN can be regarded as a time-varying topologies. For example, at time slice 1, we have the following topology. And at time slice 2, the optical switches change the circuits, and we have a new topology. Each topology will last for one time slice, and typically the duration is around 1 microseconds to 1 milliseconds. There are many path options in RDCNs. For example, in this RDCN, from TOR A to TOR B, we can use one hop path. We can also use two hop paths by traversing intermediate TOR D. In this case, when a packet arrives at TOR D, it needs to wait for the circuit. That's to say, a path in RDCN can cross multiple circuits. We can also use more hops. The question is, how should we route traffic on such time-varying topologies? Let's revisit how we do routing in static data center topologies. We use the hop count as the cost metric and apply shortest path routing. By doing so, we have a set of paths with the same length. This is called equal cost multipathing, or UCMP, which is the de facto routing policy in static data center topologies. If we follow the same method, setting hop count as the cost metric and apply shortest path routing, we will see that the one-hop path is selected. However, this one-hop path only appears at time slice 5. This path introduces a high latency and can be tens of microseconds to tens of milliseconds. The flow completion time, or FCT, is very critical to short flows. FCT is only hundreds of nanoseconds to hundreds of microseconds. Using one-hop path for short flows will make FCT much higher. If the latency is a concern, how about choosing a path with low latency? In static topologies, people use hop count to proxy latency. However, this is not true in RDCNs. The time waiting for a circuit can be more significant. Here, we define latency by using the end time slice index minus the start time slice index plus 1 and times the slice duration. It is the number of time slices a packet experiences. We need to emphasize here that the defined latency is a proxy metric to indicate how much time is required for a packet to traverse from the source TOR to destination TOR. In this case, T star is 1, so the latency of one hop path is 5 time slices, and 2 hop paths is 2, and 3 hop paths is 1 time slice. Using latency as the cost metric, we will select the 3 hop paths. Then, what is the problem here? The problem is that low latency paths have large hop counts. This will introduce high bandwidth tax, defined as the product of hop count and flow sizes. When large flows going through a long path, packets consume more bandwidth, the bandwidth tax is high, and the network is congested. So, what lessons can we learn here? First, the cost metric should take both hop count and latency into consideration. Second, path selection should be subjected to flow sizes. We propose a new metric called uniform cost to include the impact by both latency and hop count. Uniform cost has two terms. The first one is the latency of a path P, and the second term is related to hop count, alpha times hop count times flow size, and divided by B. Here, B is the link bandwidth and alpha is a weight factor. Determine the relative importance between latency and hop count term. How do we understand uniform cost? Uniform cost represents the price that A flow F traverses a path P and is specific to both paths and flows. And the flow should choose a path with the minimum uniform cost. Based on this new metric, we propose a new routing scheme called Uniform Cost Multipath Routing, or UCMP. We regard UCMP as an ECMP equivalent in RDCNs. Here we show an example of UCMP path selection. There are UCMP paths with hop count varying from 1 to 4. We have 3 flows and their flow sizes are 1 megabytes, 10, 100 bytes, and 10K bytes. For each flow, we calculate the uniform cost and this in each column. Then we choose the minimum uniform cost and select the corresponding path. Here, flow 1 choose 1 hop path since the flow size is large, and this in this case. Flow 2 selects 2 hop paths and flow 3 use 4 hop paths. It is because flow 3 has small flow size. The hop count penalty is little and latency matters more. So it chooses the path with the minimum latency. In this example, we assume UCMP paths are known. Now the question is, there are so many path options in RDCNs. How to find a path with the minimum uniform cost for a given flow? Can we simply replace the old cost metric, hop count, with uniform cost and applying shortest path routing? The answer is no. The first reason is that uniform cost is associated with an entire path, not for an edge, so we cannot use shortest path routing algorithm. The second reason is that we cannot calculate the path for every flow size. Let's revisit the paths and their properties in RDCN. Here, we list all possible paths within a top pair for a time slice. 1 dot represents 1 path. The x-axis is the hop count, and y is latency. For each hop count, the paths with the lowest latency are called n-hop fastest paths, and the globally fastest path is the one with the minimum latency, and its hop count is hmax. Among all these paths, given a flow f, which path may have the minimum uniform cost? In the definition of uniform cost, alpha and bandwidth B are constant. Flow size is given, then only latency and hop count matter here. If we fix the hop count and check the path vertically, we can see that black dots have lower latency compared to the gray dots, meaning the gray dots have higher uniform cost and will be excluded. If we check horizontally, the paths with hop count larger than hmax are not considered. These paths have higher hop count and higher latency than the globally fastest path. Now we found the UCMP path region. Formally defined, UCMP are n-hop fastest paths, and n is not greater than hmax. These paths have the potential to show minimum uniform cost. Knowing the UCMP path region, we conduct offline calculation. The basic idea is calculating 1 hop fastest path, then 2 hop fastest paths, and so on and so forth. And then stop when n equals to hmax, which is the hop count of the globally fastest path. One problem is that we cannot get hmax in advance. The solution is we compute a loose upper bound of hmax and calculate n-hop fastest path until this upper bound. Finally, by checking each path latency and hop count, we filter out the non-UCMP paths. We skip the details of the algorithm here. Please refer to our paper. Offline calculation can simplify the system design. As for online assignment, it is because the minimum uniform cost path is related to flow size and cannot be known in advance. UCMP path information is stored at Tor switches. For the online assignment, a straightforward solution is to encode the flow size into the flow packets, and then the selected path is encoded into packets header. However, this solution is impractical. First, encoding arbitrary flow size introduces a huge overhead. Second, precise flow size may be unknown. We propose bucket design and use flow agent to solve these two concerns. The intuition of the bucket design is that a UCMP path represents minimum uniform cost to a range of flow sizes. Here we show an example of UCMP bucket calculation. There are UCMP paths with hop count and latency. Using the uniform cost equation, we calculate flow size as a turning point between two adjacent paths. Same as the previous example, alpha is set to 1 and bandwidth is 100 gigabits per second. For one hop and two hop paths, the boundary flow size is shown here. That means flows larger than this value should choose one hop path, and smaller flows should choose longer but lower latency paths. Follow the same method, we calculate the boundary flow size between 2 and 3 hop paths, and between 3 and 4 hop paths. These flow boundaries compose flow intervals, and we call them buckets. For example, bucket 0 represents flow size from 0 to 25K bytes, and it maps to 4 hop paths. Then we map flow size into buckets and choose the corresponding path. Here, flow 1 falls into bucket 3, and it selects one hop path. This path selection is exactly the same as the one where we get by calculating the uniform cost. Flow 2 falls into bucket 2 and selects 2 hop paths. Flow 3 choose the bucket 0 and use the 4 hop path. According to the equation of calculating buckets, we know that at different time slices, the latency variance can lead to different buckets. So we need to combine all these buckets. The question is, how many unique buckets across an entire RDCN? Our result shows that with 108 TORs, there are 27 unique buckets, and the number only raised to 42 under 1K TORs. We use differentiated service code point, or DSCP, with 6 bits, providing up to 64 buckets, which is sufficient to represent all buckets in a large-scale topology. With the bucket design, we can eliminate the arbitrary flow size encoding. The uniform cost calculation can also be simplified by only checking the bucket index. For flow agent, we use the outgoing packets to map the bucket index. When flows start, these flows are regarded as short flows. With more data sent out, they will gradually select the paths for longer flows. Later, I will show that this design has little difference compared to the case where precise flow information is known. For the selection of alpha, we set alpha to 0 initially. Then we turn alpha according to the traffic load change. When the traffic load is high and network is congested, we should increase alpha to increase the hop count penalty. Flows tend to use shorter paths and the network is less congested. When the network is lie low, we can reduce alpha to make more flows use low latency paths. UCMP supports alpha live turning. We don't need to recalculate the buckets when alpha is changed. We have a detailed proof in our paper. Now we go to the evaluations. Here I just simply go through some baselines. VLB uses any 2-hop paths, and Opera is the state-of-the-art solution. It uses a hard cutoff of 15 megabytes. Flows larger than that value, we use VLB, and short flows, we go to low latency paths. In our simulation, we use a topology of 108 TORs and 6 optical circuit switches. First, we list some UCMP path characteristics. This figure shows the distributions of the number of UCMP paths per time slice between a TOR pair. We can see that more than 20% of the TOR pairs have more than 5 paths per time slice. Then we check the entire cycle. Around 75% of TOR pairs have more than 40 unique paths per cycle. These UCMP paths, although not many in numbers, are chosen for the purpose of minimum uniform cost. UCMP provides a wide range of high-quality paths throughout time. We need to emphasize here that UCMP is general to arbitrary RDCN circuit schedules. We observe similar results on other schedules. Then we show the hop count distribution. Compared to single-pass Opera, UCMP has 25% hop count reduction. Next, we show the FCT performance. VLB experienced high FCTs for short flows because of the long circuit waiting time. KSP experienced very high FCTs, especially 5 paths. Opera also realized high FCTs, and 5 paths is worse than single paths. For our simulation, we tried two different congestion control algorithms, NDP and DCTCP. With NDP, compared to single-pass Opera, UCMP realized 53 to 98% FCT reduction. Opera has high hop counts, the bandwidth tax is high, and the network is congested. In contrast, for UCMP, minimizing uniform cost directs short flows to longer but lower latency paths, and long flows choose shorter paths to reduce bandwidth tax. UCMP also achieves high bandwidth efficiency. We calculate the average hop count for all packets and use 1 divided by this value to get bandwidth efficiency. UCMP realized 55% bandwidth efficiency improvement. Finally, we compared the FCT performance under precise flow size information and flow agent. We see that these two curves are quite close to each other. This figure proves that UCMP routing does not require precise flow size information. We also set up a prototype testbed. This testbed consists of 3 terminal switches and 4 servers, enumerating 4 optical circuit switches and 8 TORs. UCMP still outperforms all baselines. Let's summarize here. We propose a new metric, uniform cost, to capture the price a flow uses a specific path in RDCNs. We calculate UCMP paths offline and assign a minimum uniform cost path to flows online. Simulations and testbed results demonstrate that UCMP routing realizes low FCTs and high bandwidth efficiency. We regard UCMP as an ECMP equivalent in RDCNs. Thank you.